Welcome to the Slumber Lab, where curiosity gets cozy and cosmic mysteries drifted gently into dreams. I'm so glad you found your way to this quiet corner of the universe, whether you're curled up in bed, settling into your favorite chair, or simply looking for a peaceful pause after a long day of earthly adventures. Tonight, we're embarking on a gentle journey through one of the most mind-bending phenomena in all of physics, black holes. But these aren't just cosmic vacuum cleaners sucking up everything in sight. No, black holes are something far more extraordinary. They're time machines, reality benders, and perhaps the universe's most elegant demonstration of how space and time dance together in ways that would make Einstein himself smile with wonder. Now, I do hope this exploration isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing something remarkable about how the cosmos works. And if you find this cosmic lullaby soothing, I'd be ever so grateful if you gave the video a gentle like and perhaps subscribed. It helps other sleepy scientists find their way to these peaceful cosmic voyages. Before we begin floating through the event horizons of knowledge, I'd love to know where in the world you're listening from tonight. Are you gazing up at stars through your window, or perhaps it's morning where you are, with sunlight just beginning to paint your world? Time, as we'll discover, is far more flexible than we might imagine. So settle in, take a deep breath, and let's begin our gentle descent into the beautiful strangeness of black holes. Because somewhere in the darkness between stars, these cosmic enigmas are quietly rewriting the rules of time itself, and tonight we're going to discover how. What exactly is a black hole? It sounds like such a simple question, doesn't it? Like asking what color is the scussite or why does water flow downhill? But defining a black hole is a bit like trying to describe a shadow that's so dark it bends the very fabric of reality around itself. It's not quite a hole despite the name, and it's not exactly black, though it certainly appears that way from our cozy distance. At its heart, a black hole is what happens when gravity wins the ultimate cosmic wrestling match. Imagine, if you will, the most massive stars in our universe, giants so enormous that our own sun would seem like a grain of sand beside a mountain. Those stellar titans burn through their nuclear fuel in cosmic fast forward, living brilliant but brief lives before facing an inevitable moment of surrender. When such a star exhausts its fuel, something extraordinary happens. The outward pressure from nuclear fusion, which has been holding the star up against its own crushing weight for millions or billions of years, simply stops. It's like removing the pillars from beneath a cathedral. Gravity, patient and relentless, finally claims its victory. But this isn't just any ordinary collapse. This is a gravitational avalanche, so complete, so thorough, that matter gets compressed beyond anything we can truly imagine. The star's core, which might have been the size of Earth, shrinks to a point smaller than the period at the end of this sentence. Yet it retains all of its mass, creating a gravitational field so intense that it warps space and time like a bowling ball placed on a stretched rubber sheet. This warping creates what physicists call an event horizon, a boundary in space beyond which nothing, not even light itself, can escape. It's not a physical surface you could touch or bounce a ball off. Instead, it's more like a point of no return, a cosmic customs gate that only allows traffic in one direction. Cross that invisible line, and you've entered a realm where the normal rules of physics become beautifully, mysteriously strange. The event horizon gets its poetic name because it's the boundary beyond which events cannot be observed from the outside universe. If you were to watch someone fall toward a black hole, you'd see something curious happen. As they approached the event horizon, they would appear to slow down, their image growing redder and dimmer until they seemed to freeze at the boundary forever. But from their perspective, they would continue falling, experiencing time normally as they crossed into the unknown. This is our first hint that black holes are intimately connected with time itself. They don't just bend space, they bend the flow of moments, the ticking of clocks, the very rhythm of existence. Near a black hole, time becomes as malleable as clay in the hands of gravity. Inside the event horizon lies the singularity, a point where our current understanding of physics simply throws up its hands and admits defeat. Here, according to our best theories, matter is compressed to infinite density and space-time curvature becomes infinite. It's a place where the equations that describe our universe encounter mathematical infinities and politely suggest that perhaps something else is going on, something we don't yet understand. But black holes aren't just cosmic monsters lurking in the dark corners of space. They're architects of the universe, playing crucial roles in the formation and evolution of galaxies. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole containing millions or even billions of times the mass of our Sun. These gentle giants help regulate star formation and influence the structure of their entire galactic neighborhoods. There are stellar mass black holes formed from the collapse of individual massive stars, typically containing a few times the mass of our Sun. Then there are the supermassive black holes, cosmic leviathans that somehow grew to enormous sizes in the early universe through processes we're still working to understand. And in between, there might be intermediate mass black holes, though these remain somewhat mysterious, like cosmic middle children waiting to be properly introduced. What makes black holes particularly fascinating from our sleepy perspective tonight is how they reveal the deep connection between matter, energy, space, and time. They're not just objects in the universe, they're teachers, showing us how reality behaves when pushed to its absolute limits. They demonstrate that space and time aren't the fixed stage upon which cosmic drama unfolds, but rather active participants in the play itself. Einstein's general theory of relativity, published in 1915, predicted the existence of such objects decades before we had any observational evidence for them. The mathematics suggested that if enough mass were concentrated in a small enough region, it would create exactly this kind of space-time distortion. It was a theoretical prediction so strange that even Einstein himself wasn't entirely convinced it represented physical reality. But the universe, as it often does, proved to be even more imaginative than our wildest theories. Black holes exist, and they exist in abundance. Our galaxy alone likely contains millions of them, most quietly going about their business of being impossibly dense and gravitationally influential. And here's something beautiful to contemplate as you drift toward sleep. Every black hole carries within it the story of a star that once shone. These aren't destructive forces so much as transformative ones, taking the matter and energy of stellar giants and reshaping them into something entirely new, something that challenges our understanding of space, time, and the very nature of existence itself. So, as we continue our gentle exploration tonight, remember that black holes aren't just cosmic curiosities. Now that we understand how black holes warp space-time into cosmic time machines, we need to explore their most profound mystery, how they challenge everything we thought we knew about the fundamental nature of reality. When you fall into a black hole, you don't just cross a boundary in space. You cross a threshold into a realm where our most cherished physics begins to whisper uncomfortable truths about information, causality, and the very fabric of existence itself. To understand why black holes are so troubling to physicists, we need to talk about something called the information paradox. It's not just an academic puzzle, it's a crack in the foundation of everything we think we know about how the universe works. Information, in physics, isn't just data on a computer or words in a book. It's the quantum mechanical description of every particle, every field, every bit of matter and energy in the universe. The positions, velocities, spin states, and quantum properties of every atom in your body right now represent information. And according to the fundamental laws of quantum mechanics, information cannot be destroyed, ever. This principle is as sacred to physics as conservation of energy. If you burn a book, the information isn't lost. It's scrambled into the smoke, heat, and ashes in ways that are practically impossible to reconstruct. But theoretically, every bit of information about every letter on every page still exists somewhere in the universe. The laws of physics are what we call unitary, meaning they preserve information through time. The universe might shuffle information around, encrypt it beyond recognition, scatter it to the cosmic winds, but it never truly erases it. But then black holes came along and started causing problems. When Stephen Hawking discovered that black holes emit radiation and slowly evaporate, he realized something deeply disturbing. If a black hole completely evaporates through Hawking radiation, taking with it everything that ever fell in, where does all that information go? The radiation that escapes appears to be completely random, thermal noise with no memory of what created it. It's as if the universe has a cosmic paper shredder that doesn't just cut up information, but utterly annihilates it. This creates what physicists call a paradox, a situation where two fundamental principles of physics directly contradict each other. Either information is preserved, which means something must be wrong with our understanding of black holes and Hawking radiation, or information can be destroyed, which means quantum mechanics itself is incomplete or incorrect. Neither option is particularly comfortable for physicists who have spent their careers building theories on these foundations. The paradox becomes even more unsettling when you consider what it means for the nature of reality. If information can be destroyed, then the universe isn't as deterministic as we thought. The future wouldn't be uniquely determined by the past, even in principle. Causality itself becomes fuzzy. It would mean that identical initial conditions could lead to different outcomes, not because of randomness in measurement, but because information about the initial state could simply vanish from existence. Stephen Hawking initially embraced this radical possibility. In his view, black holes were cosmic information destroyers, and we needed to accept that the universe could erase its own history. But most physicists found this idea deeply troubling. It would require rewriting the fundamental laws of physics in ways that seemed to violate everything we knew about quantum mechanics. The search for solutions has led to some of the most exotic ideas in theoretical physics. One proposal suggests that information doesn't actually fall into the black hole at all. Instead, it gets encoded on the black hole's surface, on what's called the event horizon. From the outside observer's perspective, anything falling into a black hole never quite reaches the event horizon. It gets slower and slower, dimmer and dimmer, but never quite disappears. The information gets smeared across the horizon's surface like a hologram, preserved but scrambled beyond recognition. This idea has grown into something called the holographic principle, which suggests that all the information in any volume of space can be encoded on its boundary surface. It's as if the universe is fundamentally two-dimensional, and the three-dimensional reality we experience is just a kind of projection, like a hologram. Your entire three-dimensional body, with all its complexity and depth, could theoretically be encoded as information on a distant two-dimensional surface. Another solution involves the idea that black holes don't actually destroy information, but scramble it so thoroughly that it becomes practically impossible to recover. When the black hole evaporates through Hawking radiation, the information does come back out, but it's encoded in correlations between the radiation particles that are so complex and subtle that no conceivable measurement could reconstruct the original information. The information is preserved in principle but lost in practice. Perhaps the most radical solution suggests that black holes create copies of information, violating another sacred principle of quantum mechanics called the no-cloning theorem. In this scenario, information that falls into a black hole exists in two places at once, encoded on the horizon and inside the black hole. This creates its own paradox, because quantum mechanics forbids perfect copies of quantum information. The universe, it seems, cannot have its cake and eat it too. Some physicists have proposed that black holes are connected to other regions of space-time through microscopic wormholes, allowing information to escape through hidden cosmic tunnels. Others suggest that what we call black holes aren't actually black holes at all, but something called fuzzballs, incredibly dense, stringy objects that look like black holes from the outside, but don't have true event horizons where information can be trapped. The information paradox has even led some physicists to question whether space-time itself is fundamental. Maybe space and time emerge from something more basic, a quantum information network where space and time are illusions created by the way information is organized and connected. In this view, black holes aren't objects in space-time, but knots in the underlying information structure of reality. Recent developments in quantum mechanics have added new wrinkles to the paradox. The discovery of quantum entanglement, the spooky action at a distance that Einstein disliked, has revealed new ways that information can be shared and preserved across vast distances. Some physicists now think that the information in black holes remains entangled with the radiation they emit, creating invisible quantum threads that preserve information even when it seems to be lost. But perhaps the most unsettling possibility is that the information paradox is telling us something fundamental about the nature of observation and reality itself. Maybe information isn't destroyed in black holes, but it becomes inaccessible to observers outside the black hole. The information still exists, but it exists in a realm that's forever cut off from our universe. From our perspective, the information is gone, but from the perspective of someone who fell into the black hole, it still exists. This raises profound questions about what we mean by existence and reality. If information exists but can never be observed or accessed, does it really exist? Is reality defined by what is or by what can be known? The black hole information paradox forces us to confront the possibility that there are aspects of reality that are forever beyond our ability to observe or understand. The paradox also highlights the strange relationship between information, energy, and gravity. Information has weight, not much, but enough to curve space-time. When you store data on a hard drive, you're actually making it slightly more massive. When information falls into a black hole, it contributes to the black hole's mass and gravitational field. But when the black hole evaporates, where does that gravitational field go? It's as if the universe has to keep track of ghost information that no longer exists, but whose gravitational influence lingers like a cosmic afterimage. These questions aren't just academic curiosities. They strike at the heart of what it means to exist in a universe governed by physical laws. They force us to ask whether reality is fundamentally knowable or whether there are limits to what conscious observers can ever understand about the cosmos they inhabit. They suggest that black holes aren't just dense objects in space, but windows into the deepest mysteries of existence itself. And perhaps that's the most beautiful and terrifying thing about black holes. They're not just cosmic objects, they're cosmic questions. They ask us what we mean by information, by reality, by existence itself. They force us to confront the possibility that the universe is stranger, more subtle, and more mysterious than our theories suggest. They remind us that even in an age of scientific triumph, the cosmos still holds secrets that challenge our deepest assumptions about the nature of reality. As we drift deeper into the mystery of black holes, we find ourselves not just exploring astrophysics, but philosophy, not just studying gravity, but grappling with the fundamental question of what it means for anything to exist at all. Welcome to another gentle journey through the cosmos, where we'll continue exploring one of the universe's most mysterious and profound phenomena. If you're just joining us in this sleepy scientific voyage, we've been drifting through the strange realm of black holes, those cosmic enigmas that challenge everything we thought we knew about space, time, and the very nature of reality itself. So far, we've wandered through the birth of these gravitational giants, watched matter spiral into oblivion, and pondered the mind-bending physics that unfolds at the edge of space-time. We've seen how black holes aren't just cosmic vacuum cleaners, but rather elegant solutions to Einstein's equations, places where the universe reveals its deepest secrets through the language of warped geometry and quantum mechanics. But now, as we settle deeper into our cosmic contemplation, we arrive at perhaps the most fascinating aspect of black holes, their relationship with time itself. Because you see, black holes aren't just objects that exist in space. They're also windows into the very fabric of temporal reality. They're cosmic time machines, natural laboratories, where the universe demonstrates that time isn't the steady, uniform river we experience in our daily lives, but rather a flexible, malleable dimension that can stretch, slow, and even approach a complete standstill. Tonight, Let's gently explore how these gravitational monsters manipulate time, how they offer glimpses into both the ancient past and the far future, and why understanding their temporal effects might be key to unlocking some of the universe's greatest mysteries. It's a journey that will take us from the serene event horizons to the chaotic hearts of galaxies, from the quantum realm to the cosmic web, all while time itself becomes our guide through this strange and beautiful landscape. The relationship between black holes and time begins with a simple yet profound insight from Einstein's general relativity. Gravity doesn't just pull on matter, it pulls on time itself. This isn't just a theoretical curiosity, it's a measurable, observable phenomenon that affects everything from GPS satellites to the fundamental structure of the universe. When we look at a black hole, we're not just seeing an object in space, we're witnessing time itself being sculpted by gravity into shapes that would seem impossible in our everyday experience. Imagine, if you will, standing near a black hole, watching time slow to a crawl around you. From your perspective, everything seems normal. Your watch ticks at its usual pace. Your thoughts flow at their regular rhythm. But to an observer far away, watching you through a telescope, you would appear to be moving in slow motion, your every gesture stretched across minutes, then hours, then days. This is gravitational time dilation, one of the most elegant and unsettling predictions of relativity, and around black holes, it reaches its most dramatic extremes. Near the event horizon of a stellar mass black hole, time doesn't just slow down, it approaches a near standstill relative to the outside universe. A clock falling toward the black hole would appear, to distant observers, to tick slower and slower as it approaches the point of no return. At the event horizon itself, time appears to stop entirely from the outside perspective. The clock would seem frozen there forever, its light growing redder and dimmer as it's stretched by the black hole's gravity, eventually fading from view but never quite disappearing. This temporal stretching creates one of the most poetic paradoxes in physics. From the perspective of the falling clock, or anything crossing the event horizon, the journey continues normally. Time flows at its usual pace, and the crossing happens in a finite amount of proper time. But from the outside universe's viewpoint, that crossing takes an infinite amount of time to complete. It's as if the event horizon exists at the end of time itself, a boundary not just in space, but in the very flow of temporal experience. But black holes don't just slow time, they also serve as archives of cosmic history. Because of their extreme gravitational time dilation, black holes become natural time capsules, preserving information about the universe's past in ways that might seem almost magical. Matter that fell into black holes billions of years ago, from the perspective of the outside universe, might still be slowly approaching the event horizon, carrying with it information about the early cosmos, ancient stars, and long-dead civilizations. This temporal preservation extends beyond individual particles to entire astrophysical processes. When we observe the supermassive black holes at the centers of distant galaxies, we're seeing them as they existed billions of years ago, when the universe was young and violent. The light from their accretion disks, those brilliant rings of superheated matter spiraling inward, carries information about conditions in the early universe, about the formation of the first stars and galaxies, about the cosmic dawn when darkness first gave way to light. These observations allow us to peer back through cosmic time, using black holes as both subjects and instruments of temporal archaeology. The matter currently falling into these ancient black holes left the outer regions of their accretion disks when the universe was a fraction of its current age. By studying the light from different regions of these disks, astronomers can map out the history of matter's journey from the distant past to its ultimate fate beyond the event horizon. The time dilation effects around black holes also create fascinating scenarios for hypothetical time travel. While we can't actually build a time machine using a black hole, at least not with our current technology, the physics allows for some intriguing possibilities. A spacecraft that could somehow survive a close approach to a black hole could, in principle, use the time dilation effect to journey into the future. By spending time in the black hole's intense gravitational field and then returning to normal space, the travelers would find that much more time had passed in the outside universe than they had experienced. This isn't science fiction, it's a direct consequence of well-tested physics. Astronauts on the International Space Station already experience a tiny version of this effect. Because they're in a weaker gravitational field than those of us on Earth's surface, and because they're moving at high speeds, they age slightly more slowly than people on the ground. The effect is measured in microseconds over the course of months, but it's real and measurable. Near a black hole, this effect becomes dramatic enough to allow for significant jumps forward in time. But perhaps the most profound temporal aspect of black holes relates to their ultimate fate and the far future of the universe. According to Stephen Hawking's groundbreaking work, black holes aren't truly black. They emit radiation incredibly slowly through quantum effects near the event horizon. This Hawking radiation means that black holes actually evaporate over time, returning their mass to the universe as a slow trickle of particles and energy. For stellar mass black holes, this evaporation process takes an almost incomprehensibly long time, far longer than the current age of the universe. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to evaporate completely. That's a number so large it defies easy comprehension, a time span that dwarfs not just human history, but the entire lifespan of stars, the cooling of planets, and the expansion of the universe itself. Supermassive black holes take even longer to evaporate, their lifespans extending into timescales that make the Sun's evaporation time seem brief by comparison. These cosmic giants will be among the last objects in the universe, slowly radiating away their mass as the cosmos around them grows cold and empty. In the far future, when all the stars have burned out and all the planets have frozen, black holes will continue their patient evaporation, gradually returning their accumulated mass to the void. This evaporation process connects black holes to the deepest questions about time and thermodynamics. As a black hole evaporates, what happens to the information that fell into it over its lifetime? Does that information somehow escape in the Hawking radiation, or is it destroyed forever? This question, known as the information paradox, touches on fundamental issues about the nature of information, the arrow of time, and the ultimate fate of everything that has ever existed. The resolution of this paradox might require us to completely revise our understanding of time itself. Some theories suggest that information is never truly lost, that it's somehow encoded in the event horizon or in the correlations between the particles that escape and those that remain. Others propose that space-time itself might be emergent from more fundamental quantum information, making the black hole's event horizon a kind of holographic screen that encodes information about the interior in its two-dimensional surface. These ideas push us toward a view of time that's even more radical than Einstein's relativity. Instead of time being a dimension through which events unfold, it might be an emergent property of more fundamental quantum processes. The universe might not exist in time so much as time might exist in the universe, arising from the complex interactions of quantum information and gravity. Black holes also serve as cosmic laboratories for testing our understanding of time under the most extreme conditions imaginable. Near the event horizon, the predictions of general relativity approach their limits and quantum effects become important. This is where the rubber meets the road for theories of quantum gravity, those elusive frameworks that might finally unite Einstein's geometric view of space-time with the probabilistic nature of quantum mechanics. The Event Horizon Telescope, which captured the first images of black holes, isn't just taking pictures, it's conducting experiments in fundamental physics. By observing the behavior of matter and energy in the strong gravitational fields near event horizons, astronomers can test whether time and space behave as Einstein predicted or whether new physics emerges in these extreme environments. These observations have already provided stunning confirmations of relativity's predictions. The motion of matter in the accretion disks around black holes follows the patterns predicted by Einstein's equations, with time dilation and frame dragging effects clearly visible in the data. The light from these regions is red-shifted and blue-shifted in exactly the ways that relativity predicts, providing direct evidence for the malleability of time in strong gravitational fields. But perhaps the most beautiful aspect of black holes as cosmic time machines is how they connect the very large with the very small, the cosmic with the quantum. The event horizon of a black hole has a temperature and entropy, thermodynamic properties that seem to require a microscopic description in terms of quantum states. Yet these quantum states are somehow associated with a region of space-time where, according to classical general relativity, nothing can exist. This paradox suggests that black holes might be teaching us something profound about the nature of time itself. Perhaps time, like temperature and pressure, is an emergent property that arises from more fundamental quantum processes. Perhaps the smooth, continuous time of our everyday experience is just an approximation, useful for describing large-scale phenomena, but breaking down at the Planck scale, where quantum gravity effects become important. The study of black holes has also revealed deep connections between gravity, thermodynamics, and information theory that suggest a universe far stranger and more interconnected than we might have imagined. The fact that black holes have entropy proportional to their surface area rather than their volume hints at a holographic principle where all the information in a volume of space might be encoded on its boundary. This principle, if correct, would mean that our three-dimensional experience of space might itself be emergent from more fundamental two-dimensional physics. As we continue to study black holes with ever more sophisticated instruments, from gravitational wave detectors to next-generation telescopes, we're likely to uncover even more surprises about the nature of time. These cosmic time machines aren't just passive objects to be observed, they're active participants in the universe's evolution, shaping the flow of time around them and preserving information about cosmic history in their gravitational embrace. The relationship between black holes and time also extends to their role in the larger cosmic web. The supermassive black holes at the centers of galaxies don't just influence their immediate surroundings, they help regulate the formation and evolution of galaxies themselves. The energy released as matter falls into these black holes can heat and disperse gas clouds, controlling star formation and galaxy growth over cosmic timescales. This feedback process creates a kind of cosmic clockwork where the growth of black holes is intimately connected to the evolution of their host galaxies. The mass of a galaxy's central black hole is closely correlated with the mass of the galaxy's central bulge, suggesting a deep connection between these seemingly disparate objects. This relationship has persisted over billions of years of cosmic evolution, indicating that black holes and galaxies have been dancing together through cosmic time since the early universe. The study of this cosmic dance has revealed that black holes aren't just endpoints of stellar evolution, but active players in the universe's ongoing story. They're cosmic recycling centers, taking in matter and energy and returning it to their surroundings in processed form. They're gravitational engines that power some of the most energetic phenomena in the universe, from quasars to gamma-ray bursts. And they're temporal anchors, creating regions where time flows differently and where the past and future meet in ways that challenge our everyday understanding of causality. Perhaps most remarkably, black holes offer us a glimpse into the unity that underlies the apparent diversity of physical phenomena. The same mathematical structures that describe the curvature of space-time around a black hole also appear in descriptions of quantum entanglement, thermodynamic phase transitions, and even certain aspects of consciousness and information processing. This suggests that black holes might be more than just astrophysical objects. They might be windows into the fundamental nature of reality itself. As we drift toward the end of this cosmic meditation, it's worth reflecting on what black holes as cosmic time machines tell us about our place in the universe. These objects exist on scales of space and time that dwarf human experience, yet they're governed by the same physical laws that operate in our laboratories and the everyday lives. They remind us that time itself is not absolute, but relative, not fixed, but flexible, not separate from space, but intimately woven together with it into the fabric of reality. The universe that emerges from our study of black holes is one where time can slow to a crawl, where information can be preserved for cosmic ages, where the quantum and the classical meet in paradoxical harmony. It's a universe far stranger and more beautiful than our ancestors could have imagined, yet one that remains comprehensible through the patient application of observation, mathematics, and reason. In this vast cosmic tapestry, black holes serve as both threads and looms, weaving together matter and energy, space and time, past and future, into patterns of stunning complexity and beauty. They're cosmic time machines, not just because they manipulate time, but because they connect us to the deepest truths about the nature of existence itself. Through them, we glimpse not just the mechanics of the universe, but its poetry, not just its laws, but its mysteries, not just its history, but its ultimate destiny. And so, as we prepare to continue our journey through the cosmos, let us carry with us this sense of wonder at the temporal majesty of black holes. As the cosmic timekeeper continues its relentless march, we find ourselves standing at the precipice of one of physics' most profound revelations. The speed of light, that universal constant we've come to know so intimately, transforms from mere cosmic speed limit into something far more extraordinary when we approach the enigmatic boundaries of black holes. Here, where space and time themselves begin to unravel and reconstruct in ways that challenge our deepest understanding, light becomes both messenger and victim of gravity's ultimate triumph. Imagine, if you will, a photon born in the fiery heart of a distant star, traveling for eons across the cosmic void at its unwavering pace. It has journeyed through nebulae and past planets, through the empty spaces between galaxies, always maintaining that sacred speed we've discussed. But now, in our gentle exploration of these cosmic mysteries, the same photon encounters something that will test the very limits of what we thought possible about time, space, and the nature of reality itself. Black holes represent the universe's most extreme laboratories, places where Einstein's equations push beyond the comfortable realm of everyday experience into territories so bizarre they seem almost fictional. Yet they are profoundly real, scattered throughout our galaxy like cosmic lighthouses of darkness, each one a testament to gravity's ability to sculpt space-time into forms that defy intuition. When we speak of black holes as cosmic time machines, we're not indulging in science fiction fantasy. We're describing one of the most rigorously tested predictions of general relativity, a phenomenon so well established that we can observe its effects using telescopes and gravitational wave detectors. These cosmic giants don't just bend light, they bend time itself, creating regions where the familiar flow of moments becomes as malleable as clay in the hands of a cosmic sculptor. The story begins, as so many cosmic tales do, with the death of a star. Not just any star, but one of those magnificent giants that burn bright and die young, stars so massive that when their nuclear fuel finally runs out, nothing in the known universe can prevent their catastrophic collapse. In those final moments, as the star's core implodes under its own gravity, something remarkable happens. The matter becomes so dense, the gravitational field so intense, that it carves a hole in the very fabric of space-time itself. This isn't merely a region of intense gravity, though it certainly is that. A black hole represents a fundamental alteration in the structure of reality, a place where the normal rules of physics approach their breaking point. The boundary of this region, known as the event horizon, marks the point of no return not just for matter, but for light itself. It's the cosmic equivalent of a one-way street, where even photons traveling at the universe's ultimate speed limit cannot escape once they've crossed that invisible threshold. But here's where our understanding of time begins to shimmer and dance like heat waves on a summer road. As we approach a black hole, time doesn't simply continue its steady march forward. Instead, it begins to stretch and slow, creating effects so dramatic that they transform our entire understanding of temporal flow. This isn't merely theoretical speculation, it's a measurable, observable phenomenon that has been confirmed through decades of careful observation and experimentation. The mechanism behind this temporal transformation lies in one of Einstein's most profound insights: the equivalence between gravity and acceleration. Just as time slows down for someone traveling at high speeds, it also slows down in the presence of strong gravitational fields. Near a black hole, where gravity reaches its most extreme manifestation, this time dilation becomes so pronounced that it creates what can only be described as natural time machines. Picture two observers, twins perhaps, separated by the cruel mathematics of curved spacetime. One remains safely distant from the black hole, watching and waiting. The other, driven by scientific curiosity or cosmic misfortune, ventures closer to the event horizon. As the second twin approaches that point of no return, something extraordinary begins to happen. From the perspective of the distant observer, the approaching twin appears to slow down, their movements becoming increasingly sluggish as they near the black hole's boundary. This isn't an optical illusion or a trick of perception. Time itself is running more slowly for the twin approaching the black hole. What feels like minutes to them corresponds to hours, days, or even years for their distant sibling. The black hole has become a cosmic time machine, allowing one to journey into the future simply by venturing close to its gravitational embrace and then returning to tell the tale. The mathematics of this phenomenon are as beautiful as they are mind-bending. Einstein's field equations describe how mass and energy curve space-time, and around a black hole, this curvature becomes so extreme that it creates what physicists call a gravitational time dilation gradient. The closer you get to the event horizon, the more severely time becomes dilated, stretching moments into eternities from the perspective of distant observers. But black holes offer us more than just dramatic demonstrations of time dilation. They provide windows into the fundamental nature of information, causality, and the quantum mechanical underpinnings of reality itself. The event horizon represents more than just a boundary. It's a cosmic membrane that separates the knowable from the unknowable, the observable from the forever hidden. This brings us to one of the most profound puzzles in modern physics, the information paradox. When matter falls into a black hole, what happens to the information it carries? Classical physics suggests that this information is lost forever, trapped beyond the event horizon in a region from which no signal can ever escape. But quantum mechanics insists that information cannot be destroyed, only transformed or redistributed. This apparent contradiction has spawned decades of theoretical investigation and heated debate among physicists. Some propose that information is somehow encoded on the event horizon itself, like a cosmic hologram preserving the essential details of everything that has ever fallen into the black hole. Others suggest that black holes eventually evaporate through a process called Hawking radiation, slowly returning their accumulated information to the universe in a scrambled, nearly unrecognizable form. The resolution of this paradox may require a fundamental revision of our understanding of space, time, and information itself. It's possible that the interior of a black hole doesn't exist in the way we traditionally imagine, or that the event horizon is not the sharp boundary it appears to be from a distance. These questions touch on the deepest mysteries of quantum gravity, the elusive theory that would unite Einstein's general relativity with the quantum mechanical description of matter and energy. Meanwhile, at the very center of each black hole lies perhaps the most mysterious object in the known universe, the singularity. Here, according to our current understanding, matter is crushed to infinite density, and space-time curvature becomes infinite. It's a point where the equations of physics break down, where our mathematical descriptions of reality simply cease to make sense. The singularity represents the ultimate limit of our current theories, a cosmic question mark where general relativity meets its match. It's possible that quantum effects, which become increasingly important at very small scales, prevent the formation of true singularities. Perhaps the center of a black hole contains something else entirely, a quantum bounce, a bridge to another universe, or a structure so exotic that we don't yet have the theoretical framework to describe it. These cosmic enigmas serve as more than just astronomical curiosities. They're natural laboratories where we can test our most fundamental theories about the nature of reality. The detection of gravitational waves from merging black holes has opened an entirely new window onto the universe, allowing us to observe the collision and merger of these cosmic giants in real time. Each such event provides a wealth of information about the behavior of space-time under the most extreme conditions imaginable. The study of black holes has also revealed surprising connections between gravity, thermodynamics, and information theory. Black holes, it turns out, have temperature and entropy, properties we normally associate with ordinary matter rather than empty regions of space. The entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting deep connections between gravity and the holographic principle that has revolutionized our understanding of quantum field theory. As we continue our gentle journey through these cosmic mysteries, we find that black holes challenge not just our understanding of physics, but our conception of time itself. They remind us that time is not the steady, uniform flow we experience in our daily lives, but a dynamic, malleable dimension that responds to the presence of mass and energy. Near a black hole, the future becomes plastic, stretchable, subject to the whims of gravitational fields so intense they beggar description. This malleability of time has profound implications for our understanding of causality and the nature of existence itself. If time can be stretched and compressed, if the future can arrive at different rates for different observers, then our intuitive understanding of cause and effect must be revised. The universe becomes a place where simultaneity is relative, where the order of events depends on your frame of reference, where the very notion of now loses its universal meaning. Yet despite these conceptual challenges, or perhaps because of them, black holes represent some of the most beautiful and elegant solutions to Einstein's field equations. They emerge naturally from the mathematics of general relativity, inevitable consequences of the fundamental relationship between matter, energy, space, and time. They're not cosmic aberrations or exotic exceptions to the rules. They're fundamental features of a universe governed by the interplay between gravity and geometry. As we stand on the threshold of a new era in astronomy and physics, with gravitational wave detectors coming online and space-based telescopes preparing to peer directly into the hearts of these cosmic mysteries, we find ourselves poised to answer questions that have puzzled humanity for generations. What lies beyond the event horizon? How does information escape from black holes? What happens when space-time itself is pushed to its breaking point? The answers to these questions may reshape our understanding of reality itself, revealing new connections between quantum mechanics and gravity, between information and space-time, between the largest and smallest scales of existence. Black holes, those cosmic time machines spinning in the darkness between stars, continue to whisper secrets about the fundamental nature of the universe to anyone patient enough to listen and bold enough to venture close to their mysterious embrace. In the gentle darkness of space, these gravitational giants continue their ancient dance, warping time and space around them like cosmic whirlpools in the fabric of reality. They remind us that the universe is far stranger and more wonderful than our earthbound experience might suggest, a place where time becomes a river that can be dammed, diverted, or made to flow at different rates, depending on where you happen to be standing in the cosmic landscape. And perhaps that's the most profound lesson these cosmic time machines have to teach us. That time itself is not the rigid, unchanging backdrop we once imagined, but a dynamic, responsive dimension that participates in the cosmic dance of matter and energy, space and gravity, cause and effect. Welcome to the 5th chapter of our journey through the cosmic mysteries of black holes. We've traveled far together through the mathematics of space-time, witnessed the birth of these gravitational titans, explored their strange inner architecture, and pondered the profound paradoxes they present to our understanding of information and reality itself. Now we arrive at perhaps the most extraordinary revelation of all. Black holes are not just cosmic phenomena to be studied from afar, but intimate participants in the very story of existence, weaving themselves into the fabric of time, consciousness, and the deepest questions about what it means to be. In the quiet darkness of space, black holes are performing a kind of cosmic alchemy, transforming not just matter and energy, but time itself. They are nature's most perfect time machines, not in the science fiction sense of allowing travel to the past, but in their ability to stretch, compress, and sculpt the flow of temporal experience in ways that challenge our most basic intuitions about reality. Near a black hole, time becomes malleable, personal, relative in the most profound sense. Imagine standing at a safe distance from a black hole, watching a friend slowly approach its event horizon. To you, their journey appears to slow dramatically as they near that invisible boundary. Their movements become sluggish, their signals red-shifted and fading until they appear frozen at the edge of forever. From your perspective, they never quite cross the event horizon, suspended in an eternal moment at the threshold of the unknown. Yet from their perspective, the experience is entirely different. They cross the event horizon in finite time, their clocks ticking normally, unaware of the temporal drama playing out for distant observers. This is not merely a curious effect to be noted in physics textbooks. It is a window into the nature of time itself, revealing that temporal experience is fundamentally subjective, dependent on one's position in the gravitational landscape of the universe. Black holes teach us that there is no universal now, no cosmic clock ticking the same rhythm for all observers. Instead, time is as personal and contextual as consciousness itself, shaped by the very matter and energy that surrounds us. But the temporal mysteries of black holes extend far beyond individual experience. These objects are cosmic historians, preserving information about the past in ways we're only beginning to understand. The material that falls into a black hole carries with it the story of its origins, the chemical signatures of ancient stars, the gravitational memories of cosmic collisions. From one perspective, this information appears to be lost forever, swallowed by an insatiable gravitational appetite. But quantum mechanics suggests a different story, one where information is preserved in subtle correlations between particles, encoded in the very geometry of space-time itself. This preservation of information through the holographic principle reveals something profound about the nature of reality. The boundary of a black hole, its event horizon, appears to contain as much information as the entire volume it encompasses. It's as if the surface of the black hole is like a cosmic hard drive, storing the complete description of everything that has ever fallen in. This suggests that our three-dimensional experience of space might itself be a kind of hologram, a projection from information encoded on distant boundaries. Consider what this means for our understanding of consciousness and memory. If information is truly preserved at the quantum level, if every interaction leaves its mark in the fabric of space-time, then in some sense, nothing is ever truly lost. The thoughts you're thinking now, the patterns of neural activity that constitute your present moment of awareness, are becoming part of the permanent record of the universe, encoded in quantum correlations that stretch across cosmic distances. Black holes also serve as cosmic engines of transformation, not just of matter and energy, but of time itself. Through the process of Hawking radiation, they slowly evaporate, returning their mass energy to the universe over timescales so vast they dwarf the current age of the cosmos. A stellar mass black hole would take longer than 1067 years to evaporate completely, a duration so incomprehensibly long that the universe will have expanded to near emptiness, with stars long dead and galaxies separated by distances that make communication impossible. Yet even in this far future, black holes will continue their patient work of transforming time. As they shrink through Hawking radiation, their temperature increases, their evaporation accelerates, until in their final moments, they release the accumulated energy of eons in a brilliant flash. In this way, black holes serve as cosmic time capsules, storing energy and information from the early universe and slowly releasing it across the vast sweep of cosmic time. This connection between black holes and the arrow of time reveals something profound about the nature of temporal flow. The second law of thermodynamics tells us that entropy, the measure of disorder, always increases with time. This gives time its direction, its arrow pointing from past to future. Black holes, with their enormous entropy encoded in their event horizons, are the universe's ultimate expression of this principle. They represent the final state toward which all matter and energy appear to be evolving, the cosmic endpoints where information becomes maximally scrambled and time itself approaches a kind of thermal equilibrium. But here's where the story becomes even more remarkable. The very existence of black holes may be essential for the universe's ability to support complex structures like stars, planets, and ultimately conscious observers like ourselves. In the early universe, tiny quantum fluctuations were amplified by cosmic inflation, creating the density variations that eventually collapsed to form the first stars and galaxies. Without these primordial seeds, the universe would have remained a smooth, featureless expanse of hydrogen and helium, unable to generate the complexity necessary for life. Black holes play a crucial role in this cosmic story of structure formation. They serve as gravitational anchors around which galaxies coalesce, their immense gravity pulling in matter and triggering the formation of new stars. The supermassive black holes at the centers of galaxies regulate star formation through their energetic outflows, creating a delicate balance between creation and destruction that allows galaxies to evolve over cosmic time. In this sense, black holes are not merely cosmic monsters devouring everything in their path, but cosmic gardeners tending the universe's capacity for complexity and organization. They concentrate matter and energy in ways that allow for the formation of the heavy elements necessary for rocky planets and biological processes. The carbon in your body, the oxygen you breathe, the iron in your blood, all were forged in the nuclear furnaces of stars whose formation was influenced by the gravitational architecture established by black holes. This intimate connection between black holes and the conditions necessary for life reveals something profound about the nature of cosmic evolution. The universe appears finely tuned for the emergence of complexity, with physical constants and initial conditions that allow for the formation of stable structures across a vast range of scales. Black holes are both products of this fine-tuning and active participants in maintaining it, creating the gravitational environments where stars can form, live, and die in ways that enrich the cosmos with the elements of complexity. But perhaps the most profound way that black holes intersect with the nature of time and existence is through their role as cosmic laboratories for testing the deepest principles of physics. At the event horizon, general relativity predicts that tidal forces become infinite, that the curvature of space-time becomes singular. Yet quantum mechanics suggests that the true nature of these regions may be far stranger and more subtle than classical physics can describe. The resolution of these apparent contradictions may require a fundamental revision of our understanding of space, time, and information. String theory, loop quantum gravity, and other approaches to quantum gravity suggest that at the smallest scales, space-time itself may be discrete rather than continuous, made up of fundamental units that cannot be subdivided further. In this view, the infinite densities and curvatures predicted by classical general relativity are artifacts of treating space-time as perfectly smooth, ignoring its underlying quantum structure. If this is correct, then black holes may not contain true singularities at all, but rather regions where space-time reaches its maximum possible curvature before quantum effects become dominant. The information that appears to be lost in black holes may actually be preserved in quantum correlations that stretch across these microscopic scales, encoded in the very fabric of space and time in ways we're only beginning to glimpse. This quantum nature of space-time near black holes has profound implications for our understanding of consciousness and information processing. If the brain is fundamentally a quantum information processing system, as some theories suggest, then the same principles that govern information preservation near black holes may also govern the persistence of conscious experience. The patterns of neural activity that constitute your thoughts and memories may be preserved in quantum correlations that extend beyond the classical boundaries of your brain, encoded in the subtle structure of space-time itself. This perspective suggests a view of consciousness as fundamentally connected to the information theoretic structure of the universe. Just as black holes preserve information through quantum entanglement and holographic encoding, Conscious experience may persist through similar mechanisms, creating a kind of cosmic memory that transcends individual biological existence. In this view, the thoughts you're thinking now, the subjective experience of reading these words, becomes part of the permanent information content of the universe, preserved in correlations that may endure long after the matter of your brain has returned to the cosmic cycle. Black holes also offer insights into the nature of emergence, the way complex phenomena arise from simpler underlying principles. The event horizon of a black hole is not a physical surface in the traditional sense, but an emergent boundary that arises from the collective behavior of space-time curvature. Similarly, the temperature and entropy of black holes are emergent properties that arise from the statistical behavior of microscopic quantum degrees of freedom. This emergence of macroscopic properties from microscopic quantum behavior may be a key to understanding how consciousness arises from neural activity, how life emerges from chemistry, how meaning arises from information processing. Black holes demonstrate that even the most fundamental aspects of reality, including the nature of space and time themselves, may be emergent phenomena arising from deeper, more abstract principles. The study of black holes has also revealed the deep connections between geometry, information, and thermodynamics. The area of a black hole's event horizon determines its entropy, establishing a fundamental relationship between spatial geometry and information content. This geometric encoding of information suggests that space itself may be a kind of information storage system with the metric properties of spacetime, reflecting the underlying quantum information structure of reality. This geometric view of information has profound implications for our understanding of memory, learning, and consciousness. If information is fundamentally geometric, encoded in the shape and connectivity of neural networks, then the preservation of memory and the continuity of personal identity may depend on maintaining certain geometric relationships in the structure of the brain. The degradation of memory in aging or disease may reflect changes in these geometric relationships, while the formation of new memories may involve the creation of new geometric structures in neural space. As we contemplate these deep connections between black holes, information, and consciousness, we begin to see how these cosmic phenomena are not separate from human experience, but intimately connected to it. The same physical principles that govern the behavior of matter near event horizons also govern the flow of information in neural networks, the formation of memories, the emergence of conscious awareness from unconscious processes. In the quantum foam at the Planck scale, where the very notion of spacetime breaks down into probabilistic fluctuations, the boundaries between matter and information, between observer and observed, begin to dissolve. Black holes, as the most extreme manifestations of gravitational physics, offer us glimpses into this fundamental level of reality where the classical distinctions that organize our everyday experience no longer apply. This dissolution of classical boundaries near black holes mirrors the dissolution of the subject-object distinction in certain states of consciousness, the mystical experiences reported across cultures where the sense of separate self merges with a larger unity. Perhaps these experiential states reflect a deep truth about the nature of reality that physics is only now beginning to articulate through the study of quantum gravity and black hole thermodynamics. The time dilation effects near black holes also offer profound metaphors for the subjective experience of time in consciousness. Just as time slows near a black hole from the perspective of distant observers, time seems to slow or stop entirely in moments of intense awareness, deep meditation, or profound aesthetic experience. The eternal now of mystical experience may reflect the same principles of relativity that govern temporal experience near event horizons. In dreams, too, we experience something analogous to the warping of space-time near black holes. The familiar geometry of space and the regular flow of time become fluid, malleable, subject to the gravitational influence of unconscious forces that reshape the landscape of experience according to their own mysterious logic. Perhaps the study of black holes can offer insights into these altered states of consciousness, revealing how the fundamental malleability of space-time is reflected in the plasticity of conscious experience. The information paradox of black holes, the question of whether information is preserved or destroyed when matter falls past the event horizon, has deep parallels in questions about the persistence of consciousness and personal identity. When we sleep, when we lose consciousness under anesthesia, when the neural activity that supports our sense of self temporarily ceases, what happens to the information that constitutes our conscious experience? Is it preserved in some subtle form, encoded in quantum correlations that persist even when classical neural activity stops? Or is it truly lost, only to be reconstructed anew when consciousness returns? The holographic principle suggests that information is more robust and persistent than our classical intuitions suggest. Just as the information content of a black hole's interior may be encoded on its two-dimensional boundary, the information content of conscious experience may be encoded in structures and relationships that transcend the particular material substrate of the brain. The continuity of personal identity across sleep, across aging, across the constant turnover of the atoms and molecules that make up our bodies may reflect this holographic encoding of consciousness in patterns that persist even as their material basis changes. As we probe deeper into the mysteries of black holes, we find ourselves confronting the deepest questions about the nature of existence itself. Are we fundamentally material beings, complex arrangements of atoms and molecules governed by the laws of physics? Or are we informational patterns, quantum states encoded in the geometry of space-time itself? The study of black holes suggests that this distinction may be false, that matter and information, substance and form, are different aspects of a deeper unity that encompasses both physical and mental phenomena. This unity becomes apparent when we consider the role of observation in quantum mechanics and its extension to the physics of black holes. The measurement problem in quantum mechanics, the question of how definite outcomes emerge from quantum superpositions, becomes acute when applied to black hole evaporation. Does the information that falls into a black hole remain in superposition until it's measured by the Hawking radiation? Does consciousness play a role in determining which branch of the quantum superposition becomes real? These questions point toward a participatory universe in which consciousness is not merely a passive observer of physical processes, but an active participant in their unfolding. The study of black holes, with their extreme conditions and quantum gravitational effects, may be pushing us toward a new understanding of the relationship between mind and matter, between observer and observed, between the subjective experience of consciousness and the objective structure of physical reality. In the end, black holes serve as cosmic mirrors, reflecting back to us the deepest mysteries of existence in amplified form. Their extreme gravitational fields, their warping of space-time, their quantum mechanical properties all serve to illuminate aspects of reality that remain hidden in more mundane circumstances. They show us that time is not the universal constant we imagine it to be, that information may be preserved in ways we never suspected, that the boundaries between different regions of space-time are more fluid and contextual than classical physics suggests. As we continue to study these remarkable objects, as our gravitational wave detectors reveal their collisions and mergers, as our theoretical understanding of quantum gravity deepens, we may find that black holes offer more than just insights into exotic astrophysical phenomena. They may provide the key to understanding the nature of consciousness itself, the persistence of information across time, the emergence of complexity from simplicity, and the deep connections between mind and cosmos that have been intuited by mystics and philosophers throughout human history. In contemplating black holes, we are ultimately contemplating ourselves, our own nature, as conscious beings embedded in a universe that seems almost miraculous in its capacity to give rise to awareness, meaning, and understanding. These cosmic time machines, with their ability to stretch moments into eternities and compress eternities into moments, remind us that our own experience of time, our own brief flicker of consciousness in the vast sweep of cosmic history, is itself a kind of miracle, a temporary arrangement of matter and energy that has somehow become capable of contemplating its own existence and seeking to understand its place in the grand cosmic story. As you drift towards sleep tonight, consider that the same physical principles that govern the behavior of these cosmic giants also govern the neural processes underlying your own consciousness. The quantum correlations that may preserve information near black holes also participate in the formation of your thoughts and memories. The geometric relationships that encode information in the holographic boundary of an event horizon may also encode the patterns of meaning and association that constitute your personal identity. In this view, you are not separate from the cosmos, but an integral part of it, a temporary configuration of cosmic matter and energy that has achieved the remarkable feat of self-awareness. Your consciousness is not confined to the boundaries of your skull, but extends through quantum correlations and informational relationships that connect you to the deepest structures of reality. So the cosmic dance comes to an end, and we drift back from the edges of space-time to this quiet moment. We've journeyed through the mystery of time itself, watching it bend and stretch, speed up and slow down, all while light maintains its perfect, unwavering pace through the darkness. What we've discovered is that light's speed limit isn't really a limitation at all. It's the fundamental rhythm that holds everything together. It's the cosmic constant that keeps causality intact, ensures that effects follow causes, and gives structure to the very fabric of reality. In a universe that could so easily dissolve into chaos, light's speed provides a gentle, steady heartbeat that keeps time flowing forward and space expanding outward in perfect harmony. And perhaps most beautifully, the same light that races between galaxies is also quietly illuminating your world right now, bouncing off these words, traveling through fiber optic cables, and painting the gentle glow on your screen as you settle into sleep. Sweet dreams, fellow traveler, and may your rest be as constant and peaceful as light's eternal journey through the cosmos.